Good to see everyone here. Again, I see you've made some maybe some movement here. We'll get closer to the screen. All right. So how are we doing on Zoom? Welcome everyone on Zoom. How many people are there?
Only 6, including
yourself. Yes. So 6. Right. All right. Be good from our Zoom participants to maybe raise their, maybe have a thumbs up or something to see if they're there. So if they're not just sleeping in, because they're awfully quiet, right? I would like to see at least 1 or 2 questions from the Zoom audience during these 2 sessions. All right. So our plan of attack today is do some embeddings. So today that's going to be actually, well, technically part of previous day, but actually we're going to do the embeddings and then modeling. That's the main thing. And of course, during the time also we'll do some visualizations. And during the third part today, during this afternoon, there will be also opportunity for yourself to work independently. And that will be your submission if you want to submit for the grade, for the credit. Okay, so we're going to open up the day 1, part 3. All right, so this is, again, if you have a link to our GitHub repository, GitHub 2024, let's see here. All right, it should be, let's double check if it works. If not, I'll fix it. This one here, creating embeddings. All right, and it should work. Right, so we'll connect just in case, we'll check. So for those who don't have a local installation. But again, as before, I will be working from local installation. And yeah, if you have any technical issues, we'll try to solve them during the last session. Anything, I heard a talk about some requirements file, for example. These are requirements from last year's libraries, but I'm using some newer versions, but they seem so far no problems, no issues. I don't think any issues with the libraries. Right? Everything seems to... Which one was it?
The last one yesterday about plotting the thing.
Yes.
Was MB format missing?
Okay. Oh, yes.
There was something else.
Okay, in NB format, that's a pretty common issue. You have to install it separately, basically. It's on Stack Overflow. You go there, and it's like... it's been around forever. I don't know why it's just an issue, basically. I guess nobody is responsible for it apparently, so it's just yeah, it's up to us to fix it. Okay, right. So we have our corpus, right? Yesterday we went through, we had a file, we unzipped it, we extracted the structure, we had an XML file, we extracted some features, we have some words, and so today our first part will be working on embeddings. So what's an embedding, really? Really, it's a numerical representation of some textual data. So it could be, what could it be? It could be embeddings of words. So each word, or tokens are words in this case. So each word gets a numerical representation, a vector. So we could say a bunch of numbers to say, but not to use mathematical language. And the embeddings could be also for sentences, could be for whole documents. But the whole idea is we have numbers, floating point numbers, meaning we have real numbers, which are used by basically all kinds of algorithms, machine learning algorithms and other algorithms, because computers basically can't really work with a string or a textual, just a text, right? Because again, behind every letter, every character, of course, there is a Unicode representation, at least if you think about it, right? So, I mean, computers don't really work on a symbolic level as such, at least the ones we use here. Right, so we will need to use, today we will want to create these vectors. We will be using them, right? And then we can do all kinds of cool stuff. We can find, for example, similar words with similar meaning. Right, we can use things like cosine similarity to find things which are similar. We can use some other methods as well. Right. So yeah, it mentions here in our notebook. Right, it works better with numerical data. Actually, that's basically the only way. Right. In fact, it's interesting thing is, yeah, if you are building your own large language model, you'd also want to have some word embeddings. Actually, right. So Yes, but there are many different types of embeddings, and we'll start with the simplest one, which of course is famous bag of words. Basically, we are going to basically count the times the words appear in our documents, and basically, just have the numbers for that, right? So Valdis appears 5 times. Valdis gets assigned some index and also value 5, just to get started with that. Something really simple like that, right? But then we'll maybe move on, assuming we have time. We'll move on something more interesting things like word2vec, which is a really cool embedding model and still works really well and it's fast. And we won't get to Bear today probably, but it's also still very relevant actually. Right. So again, this is your first step if you're going to do any sort of advanced analysis or anything you want to do with your documents, your words, you need some sort of embedding, basically. Right. Again, bag of words, it's been used for a long time. It's like the first step, so that's where we're going to start. Let's see. Now, so we will use the same data set. Let me see, I'll import, let's see what we have, pandas, and we will be using GenSim. GenSim is a great library for topic modeling. Who has used GenSim? Anyone? Yeah, 1 person, 2 persons, great. All right, so developed about 10, 15 years ago in Czechoslovakia, I believe, and it's still being updated. So so this means some of the more advanced algorithms, we don't have to read the paper, we don't have to re-implement ourselves. That's one of the big progress being made these days is that 10 years ago, 15 years ago, you had to read the academic paper, and you actually had to implement the algorithm, right? Maybe you had to write in C, but now, even Python, but now, well, it's done for you, right? All you have to do is plug in some, prepare the data, prepare some hyperparameters, and off you go. So that's a big advantage for us who don't, for those who don't want to really, go really that deep. It's an interesting topic, of course, right? So also we'll use scikit-learn, which is a great machine learning library. But for now, we'll use it just to create the TF-IDF embeddings. And let's see what do we have here. What versions are using? T12. And let me just for a heck of it, well, not for heck of it, but for a double check, see what we get here. It should work, right? Let's see, connect. I am connected. Yeah, I'm connected. Let's see what works. We can compare the versions. Pandas 432, 122, right? What do we have here? 1.0, 433, 222, right? So my computer has slightly more, newer versions, but it should work. It should work on both versions. Okay. Sometimes, of course, some tiny things like API changes, some sort of, some documentation change. There's some tiny changes made, but these are pretty stable libraries. So, all right. So now we need to get the data, right? We need to get data, and we have I'm going to use Parquet file. It should work. I think everybody got Parquet working, I hope. I mean, reading, it should work, right? Saving sometimes may have problems, but reading, it should work, right? So let's try it. Again, we're going to use a URL address. Again, that's why, so it should work for everyone. Of course, generally, when I work, I use a local data source. I don't, reading from a URL from web resources, if you work loading a 100 gigabyte file, it can get pretty slow, right? So you want some local resources usually. But here for our workshop, we're using a URL, so it should work for everyone. Let's take a look, assuming you have a network connection. It should work slower for me because, of course, I'm using mobile connection today, so hopefully, but it worked, right? I wonder how quickly did you load it? It should be much quicker, right? Like a couple seconds? 15 seconds? Also slow, right? Using that Wi-Fi, right? Yeah. Yeah. Yes. So it should be here, of course. I assume if you load it from here, it should be quicker from the Google, right? Because here, yeah, it was almost instant, right? Because I guess Google has better connection to the GitHub, right? So, all right. So we can check a couple things first, so how much memory we're using, things like that. Actually, right, roughly it says 5 megabytes, not too bad actually. Actually have storage used. Let's see, this is just extra some information. Again, let's see what we have as variables. What do we have here, right? We have data frame and we have a URL, right? That's all we have right now, right? And again, we have the shape, info. Right, let's see what actually we have. Do we have how many? We have 9 columns, right? That's good. Let's take a look what it looks like. Right, these we know. Okay, we have a trial number, punishment, dirty length, clean length, words, word count cleaned, word count before, after, and we also have words lemmatized, right? So, and again, we can get our basic statistics. Let's double check if there's anything missing. This is for the numerical columns, right? And let's take a sample. This is not absolutely required, but this is basically we set a seed, so we should be getting the same sample. I don't know if it's going to be the same sample here. Let's take a look if it's actually going to be the same one. Yeah, it is exactly the same one, right? So, as you probably know, our computers, when we look for a random number, it's not really random, right? It's so-called pseudo-random numbers. So, if you sort of need to have these pseudo-random numbers in an exact same sequence, you can set a seed, and then you'll have always the same randomness, right? It's like that old joke about always getting the same number, right? You know, it's so if you need true randomness, what do you need to do? You need to observe some atomic process, or maybe look at lava lamps. There's some random processes which are more random than what we use here, right? So, okay, so now let's see, we have our data, we have trial number, punishment, and we will want to look here. I'll close this here. Let's take word lemmas. So this is actually a list of words, right? There's some numbers here actually, so words and word lemmas actually. And let's see what we looked at histogram, I think, yesterday actually. So this is nothing. We know that most of these there's one big document and the rest of them are just small, short documents. Yeah, there was that one really long, which ended up with the sentence, this one outlier. Typically, I like to look at the outliers, see what's going on there. Sometimes it's the outlier actually there's something wrong with the data. Maybe there's two stories stuck together, things like that. But this actually, it is a pretty long, 11,000 words. So this is a big trial apparently. Well, it ended. It was apparently there's a death sentence there. So for this history, yeah. So we can skip, of course. We can skip. We can say, okay, we can put a filter again for those who are new to Pandas. Pandas has a very handy way of putting filters. You say, okay, you have a column name, assuming it's a single word, the column, and you say, okay, you want what the requirement is, and then that's going to be selected, basically. It's going to be filtering for that. So we can see the short histogram again. But that's just still getting ready. Okay, all right, and maybe we can also do a histogram with bins. Histograms, of course, right? We can see better there. All right. So again, we can see the short documents. This is some extra visualizations, so not crucial again. So the thing is, now when we see our embedding or lengths, why am I doing this? Because we might not have enough information in our text to do a good embedding model. All right? We have, if it's a 5 words document, unlikely we'll get much useful information out of that. Especially because remember we removed the stop words yesterday, right? So maybe it was only like 5-10 words, right? But let's see how many actually, if we have time, let's take a look how many really short ones we have, right? Let's take a look one more thing. Let's look at on this maybe to demonstrate, see how my A assistant works today. Copilot. Let's look at clean words. Let's see, how did I call this column? Word count cleaned. Let's look at word count cleaned. Like look at rows that have less than let's say 10, right? And let's see what it does. Yes. Exactly. AI knows what I'm talking about. Immediately, it gives me the right filter, right? It's because why does it work? Because of course, Pandas is a popular library, and this type of operation is similar operations have been done, right? So again, obviously, with the AI model, maybe this particular incantation was not done exactly before, but there is something similar. So it's very likely to be good. So shape, let's see how much shape is, right? Let's see, yeah, shape. Oh, I'm sorry, shape is this, right? You see what happens. Yeah, only 11 really short documents. Okay, not too bad actually. So now we can do, okay, so let's do this. Let's look at a histogram that have not less than 10, right? But 50, right? Let's use how many bins? Let's use, yeah, okay, why not, right? So that's all immediately, right? So I saved myself, I don't know, 20 seconds, right? So it should work. Right now I can see what's happening here, right? So that looks pretty decent actually. So there seems like a nice peak there, of course, but then it levels off. So these really short ones are not to present too much. Again, warning for those who are using histograms, the number of bins can make a big difference you use, right? You can you can have all kinds of fun with statistics and therefore histograms when you select a wrong number of bins, basically. So it might appear differently. That's why kernel density plots are usually suggested for more to give you a more accurate presentation. So let's do this actually. Let's do that. One more. Let's create a kernel density plot of word counts of, what do they call it? Of word count clean for documents with less than 50 words. Again, AI thinks that's what they want to do. Obviously, if I don't want 50, I want to put 100, I can put, I put 60, for example, right? And we'll do that, of course, and it will do the same thing. Plot key D, and let's see if that's enough, right? It should be, again, for a quick one. And we have a nice kernel density plot, right? Again, so it smooths out this, so you see a more accurate representation. Obviously, there's no minus 20, right? Kernel density plots work differently. There's a kernel density function which sort of smooths out the plot. But it's similar representation as histograms. So let's do this over. Let's see if we can do this. One more thing before we move on. Let's see if we can make it plot both on the one same. So let's plot both histogram and kernel density plot on the same plot, for documents is less than, let's say, 60 words, okay? And let's see how it works. Let's see, it's gonna work. I don't know if it's gonna work like this. I'm a little bit suspicious. It's gonna put them all together. We might need to do some extra things. I think it's gonna take 2 plots. Yeah, it's not gonna work. Or it actually works, but we might need to, the plot, of course, that there's 2 axes. Remember, and let's use secondary y-axis. Okay, let's see that happens. Let's see what happens now. All right, and yeah, and let's see. I'm not 100% sure here too, but might work better. Yeah, much better. Yeah. Again, why am I doing this? Because matplotlib, which is running here underneath Plotly, is notoriously huge library, difficult to work with, and has so many settings. They have improved quite a bit in the last few years, matplotlib, but still, like 3-4 years ago, it would have taken me maybe 10-15 minutes to come up with this. Right, look at the documentation, look at the multiple. I mean, it's still nice. It's nice, but again, it's much quicker now, of course, to use the AI assistants to do this type of thing, assuming you know you can do it. Now, of course, you can do this also for more serious graphs. I would switch to Plotly, which make nicer graphs. These are just for quick exploratory, get the first feel of the data we have. Again, I recommend doing this because you might basically be working with the wrong data. Maybe you have some really strange outliers, maybe something else, and before you do all this fancy embedding, create this fancy model, and you end up with bad data. But again, so this data looks pretty normal. I mean, assuming this is it. Again, of course, there could be some hidden gotchas. Always there could be some hidden, imprecise data somewhere. Okay, so yeah, we have so let's see. Maybe we'll do some cleaning now. Concern a short text. I mentioned this, right? So we could remove the digits again. We can do this. I'm going to use apply, but of course there are other ways of doing this. But so I make a word for word in words. If not, word is digit, right? So I'm going to remove numeric words basically with this recipe. So again, this is something you should discuss. That's why we have notebooks. Is there maybe reason to keep in these numbers? They might be useful for some analysis, maybe for analyzing what kind of maybe there's money issues, maybe some other things, maybe some numbers can be useful sometimes, right? Especially if you're trying to find some price information, things like that. Obviously, you will need the numbers there. But for our purposes, I'm going to just remove the digits here, right? Again, with apply. And let's see how many, what's the word count, clean, no digits. So let's take a look, and also we'll figure out with this recipe how many did we remove. Let's take a look. Last time it was 408, I think. So 12,000 words, which are actually just digits, basically. Yeah. Right? Because of course. So let's take a look if this happens. Yes, it's still same, right? Still 70, right? So now. Yeah, we could merge, of course. Also, next step is maybe we want to remove, which we didn't do yesterday, is remove numbers from words. So you have like 5D, maybe Valdis 6 or Valdis 7. Again, this could be OCR errors, so just our numbers. Sometimes they're stuck to the word, to the token, right? So this next recipe will remove actual digits from a word, right? Again, maybe you want to leave them in, right? But this is basically, we can test it, how it works, right? So you see, after testing, this is empty, ABC is clean, 456 is done, while this has no 2023, let's make it 24, right? Right, to make it, and also these will also be gone, right? Okay, so let's remove words with digits, right? Yeah. This actually is a function which could do it, same thing. Let's take a look how many it works. Only like 1600, right? So, or 1900. Okay, so there's actually 1900 words which had some digits. Okay, now, again, this might not be necessary. Maybe you want to keep those words, right? But now, so you could skip this session, the previous section, but let's now move to bag of words. Right. So we are going to count how many times each word appears in a document. I'm sure some of you have used this bag of words method, right? But again, I think we can use, I'll use a count vectorizer. This is from scikit-learn, right? Otherwise, we could, of course, use something like a dictionary counter by yourself. But again, then there's no need to reinvent the wheel, right? Basically. So we're going to initialize this vectorizer, right? It has some extra parameters, actually. You can set encoding. You can actually supply. The thing is, since this is such a common task, you can supply your own, the things we did before, such as stop word removal, things like that. You could supply them here to this object, basically, when we create this object, count vectorizer object. So the way it works is, for those who have taken Python, know what the Python class is, right? There's a Python class, and we create an object out of that, make an instance of this class, create a count vectorizer object, and then we get the nice methods to do something with it, right? So let's see what else. There's ngam range, there's max, there's some max features, things like that. But for now, we're using default values. The one thing I like about scikit-learn library is it usually has nice, decent default values. Scikit-learn, right? Great, one of my favorite libraries for making prototypes, at least, is It has good documentation and covers all the basic machine learning tasks. I mean, it has a, not only basic ones, it covers also some advanced ones as well. Right. Okay. Now, so we create a count vectorizer, and all we have to do is fit. So this will be very common when you deal with any machine learning topics. In general, NLP tasks, of course, so fitting is basically we run it, basically, but very commonly done. So let's see, do we have to do anything else? I think that's it for the vectorizer. Yes. Now let's take a look. Words lemmatized, apply, join. And yes, so we are sort of going backwards here. Let's take a look here. I think that's the case, right? So we have our words lemmatized, this column here. Let me take a look at, let me show you what we're going to be doing. Escape B. So let's show first 5 rows of our database, of our data frame. Thank you, AI. Again, sometimes you think it picks up what you're speaking, but no, it's just a text predictor. Right, so obviously they have head on, we see here, right, we see these here, right. So in a way, since I don't have, at this moment, I don't have this, well, I have it here actually, but this is not clean. So the cleanest one is this one here, right. And this is what we are going to be creating bag of words from, right? So in a way, I'm going back to this representation here in this step, right? If you check this here, this part here, I'm going back. So I could have made this beforehand, actually, right? So I'm joining back this. So I make it back, and then again, a vectorizer fit method will do it for me. Again, it will split them again, sort of. Again, sometimes this happens. I wonder, maybe, again, this might be assignment, maybe there's a way to skip this. Maybe there's a setting which says, okay, you're getting a list of words, and that should be already, there's no need to do it over, right? So we're doing this redundant part for 1,600 rows, 1,600 documents, not a big deal. It's going to be fast. If you have a couple million, you might want to do this beforehand. You don't want to do it twice, right? It might slow down things. Right, so let's take a look if this works. So this is actually what's going to create this vectorizer. And let's see, it builds a library. But is that going to be all? I'm not sure. Okay, so yeah. So we have 18,093 words, right? So what happened here, right? Word count, right? So this Leonard is cheap in dict. Right, you see steel, pound, tobacco apparently was a very popular thing to steal, right? And prosecutor, of course, so there's actually some things which you would consider stop words almost. The prosecutor, of course, I would imagine it's not going to signify anything when we want to predict whether somebody had a bad sentence. It should be always present, actually. It's almost like for particular, could be for this case, could be maybe taken off. You have to see if it's always present, might not be very useful, but we'll see later that can be handled with TF-IDF, of course. Right, so this is, okay, so we have our vocabulary from count vectorizer. We can count the words, right? We already did that. So, yeah, words lemmatized, right? Right, let's see. These are my words, right? So now, yeah. Okay, so now we are actually going to do, we can create a representation of this. So this first fit we did here, they just created a bag of words for all of them, created the dictionary. Now, let's create actual vector. For now, I will be doing it with a single document, right? So this one, first doc, right? Let me show you what I'm doing here. So this is the first or first document, right? So this one here, right? Yeah. Again, right? That's what we have, right? And let's see what happens here. And I think it's a sparse matrix. And yeah, okay. So what's a sparse matrix? Who can tell me? how does it compare? What's a matrix, right? So matrix is two-dimensional. Yeah, two-dimensional array, yes. So if vector is one-dimensional, so two-dimensional array, basically, you think. But sparse matrix, what does that mean? Anyone? Any ideas? Sparse. What does it mean? Excuse me? Yes. So lots of missing data. So idea is this. If you have a dictionary of 18,000 words, right? You don't want to usually for space, saving space, if you have, especially if you're processing a lot of data, you don't want, there's going to be a lot of zeros, missing value, no hits basically, right? So in this case, we know we have a very short document, 60 words, right? Obviously, the other 17,000 something words will be not present, right? So that's why scikit-learn, this vectorizer, is returning not a full matrix, but just sparse matrix. Again, so it's like so it says 44 stored elements. So apparently there were some doubles there, right? And actually there's some single letters actually, right? I notice that might be something to clean. But yeah, so that's what sparse matrix is basically, right? So the thing is with sparse matrices, some things don't work very well with sparse matrices. So sometimes you want to convert them to full matrix. But you can, so this is basically what we have, right? So when I print these indices, right, I'm printing the actual representation. These are the indexes, what the word means. So basically, again, for computer, does not know at this stage when you're working with words, the computer doesn't want to know word, meaning of the word. It just wants to know, okay, just a number, right? So, and I touched on this. I don't like these short words, right? They were probably either, again, OCR errors possibly, or maybe they had that money, right? And for this, yes. So they might have represented something. Again, this might be something for your own. You might want to keep them and do some analysis on that. What's there? Any ideas what it could have been? Anybody? I don't know. Those numbers. Again, that might be something for the extra session, right? Yes, maybe shillings. That's a good hypothesis actually. So maybe some penalties, or maybe how much was stolen. Maybe that's also, or how much damage was done, possibly. Right. L, I don't know what L could stand for. It could be just one. Maybe it's again could be. You could check. Right. So let's do this. Let's remove the shortest ones. Keep the minimal word basically. Again. Yes.
In sparse matrix, why is it 44 numbers but not 60?
Yes, good question, because I think they're doubles. Let's double check. Let's double check their doubles in there. So what I'll do is I'll do this by hand, and let's see if hypothesis is correct. So I have my first doc, right? On I don't know if Vic appear, prosecute servant. Okay, let's take a look. Okay, so we have first doc. Right, let's see how many unique words are in first doc, right? So this will be a set, right? So it's document, right? So let's see what the AI does for me. Yeah, len set first doc. Simple Pythonic way, right? And of course I can do this, I'll do this even like this. Print, print unique words in first document, right? This again, AI makes my code slightly more readable. If I didn't have AI assistance, I'd probably just write this part here, right? But with AI, I can get a nice little setup here. I don't have to type, save myself 10 seconds, right? So again, yeah. So 47. That's interesting. So what happened to those three settings? That's much more interesting now, right? It seems like roughly okay. It's possible. There was something missing here, right? So maybe if it's 44, but let's check let's check when we did this part here, transform, right? Okay, let's take a look here. Right, documents, so string, right? We have vocabulary, right? So that my hypothesis, why there's only 44, not 47, You know why 47, it makes sense, right? Because there's some doubles, right? I think the dictionary, when we build this dictionary, let's take a look at this. It has many hidden settings, or we call them parameters, right? And let's take a look what's here. It might be max features. No, let's see. I'll probably look at the. I think so. That's what I'm thinking. That's what I'm thinking. That would make most sense. Let's see now. Yes, then our hypothesis, I think, is, I would say, 99% proven, right? So, does it now make more sense? Why we have 44? Or the scikit-learn, the vectorizer, the default setting skips the one length letters. So then we get to 44. And of course, this is again, at each step, I recommend putting some checks to see if there's some discrepancy, right? So again, and especially again, if you're working on a longer processing pipeline, you need to put these extra steps. So,
But I have a question.
Sure.
For the sparse metrics, since we have double words or words appearing multiple times,
Yes.
is this information missed in the process, or it's just present versus?
I think this is a binary. This right at this moment it looks here. This is just binary. Yes, no, yes, no, yes, no. But of course, we could make, of course, counts. Of course, that would be, of course, completely valid, and it might be actually more. If there's something is present 5 times, again, it'd be much more useful information. Maybe it could obviously have some relevance, right? But for now, this is just simple binary yes, no, or false, true, false setting, right? So yeah. Now, we have these indices, right? So yeah, we can remove the 4. Yeah, so that's something we could do, but it's already done. So if you want to know the first bag, and this is something I had to change if they change this get feature names out. So this is one of those things when AI was suggesting me a method which was changed, which was depreciated. So there's a new method. This is a new method. Apparently, let's take a look. Yeah. All right. So this method is basically, so you don't have to do this by hand. So these numbers, it looks them up. Okay, what is 583? Right? It looks up. Okay, it is a pair, and so on and so on and so on. Right? So if you need to, again, if you want to check, again, sometimes in the middle of this big process, you check, okay, what am I doing here? Are these actually the actual right words, right? And so on and so on and so on. All right. So, right. So, let's get second document, right? We'll see that again. So, if you want to do some comparison of these documents, we could have this huge matrix for every document, right? And we could compare them, things like Jacquard similarity, sets of check them these yes, no, and see if they're similar. But it's not likely to be a good approach, not likely to work very well for our needs. So again, we can do a second document, right? I'll show you how it could work. So again, we have some second bag of words, right? And we could compare them, right? I'll show you how it's done. Again, for those who have not seen this Jacquard index, right? Basically, we compare, right? This is made like late 19th century and used quite a bit, right? So we have 2 sets of samples, and we can gauge how similar they are, basically. And this is a formula here, right? So a union of both sets, and divided by number of A and B minus union again. I think, yeah, that's what happens. Which is of course, not this junction, but this junction, right? This junction, right? Or intersection, right? Intersection, right? Yeah. Intersection on union. Sorry, yeah. Intersection union. Yeah, U. Right, that's how you remember it, right? That's union, right? That's intersection. So U is actually union, right? Okay. Right. So used quite a bit, right? You can see some examples here, right? So that's what we could do here. I'll show you that here's a simple way of doing it. So length. That's how we implement this. We have a first bag, right? We provide 2 bags. two bags of words, right? Set of one on other, right? So let's test it, right? And we could basically get a Jacquard similarity, right? So 0.22, about 0.2, right? I think the range is going to be always from 0 to 1, meaning, I believe so. Let me double check if I'm, yeah, from 0 to 1, yeah. No, that's the maximum, minimum. Yeah, so 1 would be they're basically the same. They all have same information, so basically it'd be exactly the same. So what's the downside to this? Well, of this way of creating this Jacquard similarity, of this, you have these two sets of some information, right? This is well-established principle, but the problem is if you have a lot of many rows, these set operations actually might be slow. Actually, creating everybody versus everybody. You might have this. Let's say you have a million documents, right? Let's say, and you have embeddings for them, no problem. And so you have this. Let's say it's bag of words for now, and you want to say, okay, which ones are similar? This means you have to do fill out this huge table, million by million. That's trillion, right? Well, trillion divided by half. You don't need the, you don't need the full table, but you need the half table basically. And still, that's a lot, right? So not feasible. It's feasible for smaller sets like this example here, but it's not feasible for larger sets because you have to just do a very computationally extensive, right? Okay, so that's the downside to this. But yeah, so let me write this a little bit here. So let's see. So with Jacquard, the minimum, yeah, exactly, 1 would signify, yeah, exactly, thank you, AI, on while 0 would signify the two documents have no words in common whatsoever. Yeah, thank you, AI. All right, so, but yeah, downside to Jacquard, yeah, that's also frequency, like you mentioned. That's one side. Another downside is that for large corpuses, yeah, exactly, because we have to generate, yeah, exactly, yeah, in both documents. Oh, right. So, okay. So those are the downsides. Okay, so next thing is TF-IDF. I'm sure some of you have encountered TF-IDF. So this is going to give you a better representation. Some of you have, right? TF-IDF. And idea is this. You have term frequency. That is how many times the word appears in the document, right? And inverse document frequency, right? So idea is this, that we penalize the words which appear everywhere, right? Persecutor, right? It's going to be in every document, so it's not going to be likely significant. And this technique actually has been used quite a bit for search. All kinds of search engines use this approach. It works quite well, actually, right? So TF, how many times the word appears. On the bottom is IDF, number of times number of documents in a collection that contain a word. Right. So if IDF is high, this means the word is not particularly common. If TF is high, this means word is common in the document. Right. So let's do this. But again, in this workshop, we don't have to do this by hand. You could try to do it by yourself, write your Python code, but we don't have to do this. We can use a TF-IDF vectorizer from scikit-learn, and it works quite well. So again, I'll be using default vectorizer. Again, for your assignment, you could see, maybe play around with some of the values. Again, you can supply, I think you can even supply encoding, of course. This should be very important if you're doing some non-English words. Decoding error is what to do if there's a decode error. Accents, you can strip the accents. I don't know if it's going to work with Latvian, I don't know. Again, I usually tend to do all this beforehand myself, right? But you could do this here as well. You can supply tokenizer, a custom tokenizer, stop words. You can supply stop words. You can supply your own. What is a string? This is part. Look, this is actually a default value So that's again raw regular expression, raw string, which is here is regular expression. Let's take a look. So word is what? At least 2 letters. If I'm reading this correctly, right? One word. I mean one character, right? Or let's take a look, right? That's what makes.
It is 2, yes.
Yeah, it's 2 because plus means 1 or more. So it's saying one more, and maybe then 2 or more, basically.
Yeah, but it's only the ASCII characters, isn't it?
Yes. Here, well, no, it should not. No, I think it will. There's a setting. Well, let's see. It should work also for picking up also any. This depends on the engine. Of course, depends on the engine, right? But generally, it should cover also cover words from other language. I don't know how it works with, let's say, Chinese or maybe, I don't know, Arabic. I don't know about that. But for regular language, it should pick up. So, we are here. Again, what didn't check here? Right, so n-gram range. I think we can supply also whether we want n-grams. I believe so. So what else? Vocabulary. Right. Meaning for now, we're just going to create single words. There's also normalization, use IDF, smooth IDF, okay. Now, right, so it's like count the vectorizer followed by TF IDF transformer. All right. Somebody's coming in, okay, now. Okay, so let's try using it. Again, it's very simple to create an instance, right? So here is this where you will play with some custom parameters, right? And now we'll create, again, as usual. I'll take my words, and again, I'm going to supply the string of actual I'm going to, again, out of my list of words, I'm going to supply it back as a single sentence, basically, or single document. Now, again, I would be interested to see if you can actually skip this part. Again, maybe you could do it immediately and supply just the lemmatized. I know I tried it, and I didn't quite work, but so again, it's going to join, and this fit is also going to split it as well. Now, let's take a look what we have. Okay, again 1803. Again, right? I think the numbers. Since it's going to did this vocabulary was made. It's going to probably be the same indexes. Let's see, 15110, Leonard East. Right, that's for first one. Right, these are first full vocabulary, okay? Right. Same vocabulary. It makes sense, again, because as it is mentioned, if you read it carefully, the TF-ID vectorizer is using the count vectorizer first to build up this vocabulary. Well, it's part of the process. It's just a longer pipeline. So now we have our vocabulary. We need to build this actual embeddings of TF-IDF. Right. So let's use, again, it's going to be using transform method. So again, we'll try it on the first document. Before I go through all of them, I'll just get first doc on. Again, it's going to be, again, probably sparse matrix. I believe so. Let's take a look. And yes, again, we have sparse matrix indexes. Right. So let's see. I think a set of intersection. It's going to be exactly same, I believe, right? For now, right? Yeah, let's see our data. So indices are same words are exactly, but now we actually have our data, right? So sparse TF-IDF sparse matrix, we actually have a data, and this is now how long do you think this matrix is? I mean, this vector is? How many values? 44. Yes, of course, right? Because we have 44 values, right? Again, we skip those short ones. We have the duplicate. So each unique term in this document gets this value. And again, in order to calculate this, of course, you had to go through all the instances of all the documents, right? So, max 5. That looks like the most important one, and we can use NumPy to look for the most important words, I believe, right? Yeah, that's going to be indices of most important words. right? And let's see what they are. What are they? 15. Yeah. So can we? Okay. So that's what I'm going to try to get it right. So let's see what they are. So these are the indices, right? And yeah, get features out. So I'm going to supply these indexes, and I'm going to see what they are. So these apparently, tobacco, still important actually, right? So perceive, Leonard, servant, is cheap, paper, confess, depose, job, wick, tobacco. So tobacco is important here, right? So, and we could, this is another recipe, we can just print them out what they are, right? So perceive, Leonard, servant, is cheap, paper, confess, depose, job, wick, tobacco. This is just to see what, what's happening. Obviously, when you're doing larger analysis, you don't need to print out everything at each step. Now, let's get top 5 words for each document, right? So we're going to create embeddings for everything. And create a function, right? We pass a document, we transform it, and get indices of top n words, right? So, and then we can see, provide a document, n, I supply, how many you want, basically, right? And let's see if this works. Yeah, tobacco, it works. Okay, so how about, let's try it on second. Let's see if AI is good enough, if it's paying attention to what I'm doing. Let's do it. Let's do it for second document. Yeah. So do it, right? Context. Yeah. Second, smart. Okay. And it should pick up on this. Yeah. Get top words, right? And we will see the top 5. Let's do it. But get. Let's see. And let's see. Make it work. And get top 10 words. Okay, so this part, let's see if it works. And it works. It picks up on my hyperparameter, my argument, and of course it works fine, right? So now it works. Yeah, and this is for a second document. Hat. Yeah. Bermudas. Bermundas. I don't know what that means. It is maybe Bermudas. I don't know. Fetched. Right. Shop. Cornhill. Right. So now we can apply to our data frame. So what we can do, of course, is we can get top 5 words for all of them. Again, this would not be very quick on a large data frame. We have 1600. So again, we can use this apply method, right? There are other ways of doing it, but for now, apply. And I say, okay, get the top words, n is equals 5. Let's see, why am I using lambda? Why can't I just do it directly? I'm trying to see, why do I need lambda if I only have a function? And good question. Because I'm doing 5. Yes, so I'm thinking, yeah, okay, that's what I'm saying. Yeah, I could do this, right? Yeah, so this would be a way if I need to pass some other value, right? If I just do this, yeah, this I don't need this. This would be maybe for 10, right? This would be fine. That's what I thought, right? Yeah, yeah.
We can supply parameters even without lambda.
Yes, there should be. I think it was here, right? It was. You could do it here, right? Yeah, and args. Yeah, you supply a tuple. Yeah, you supply a tuple here, I think. Yes. Yes. Okay. So you could supply, I guess you could do this, right? Let's try it. So, but, yeah, it should work. So it's not top 10, right? Let's see if this works. Let's see if this works. Maybe it's going to break. Okay, future. Oh, yeah, convert the type, but looks like it worked. On the first try, we'll see.
I think it also works without the brackets.
Maybe without brackets if you have single? Yeah, because if you have multiple, but it said tuple, right? So maybe you just, yeah, maybe it might work. Taking a while. Because we're doing it for every single document. I didn't check how many times it was done before. So this is a little bit of an experiment. Yeah, it worked. It's 38 seconds, and of course I now have so I don't have top 10, but now I could do top 10. Let's see what we have. Let's see what we have. Let's see what we have, right? And it should pick up. Well, yeah, okay. No, let's do it afterwards. Okay. I don't want to do it. I want the AI to do it for me, right? So let's see what we really have. We need yeah. Okay, but that's a sample. So it took a sample of 5 and it got me just the top 10, just a single column. Right, it works, right? So sample, right? Yeah, coal, right? Old, long, food. Okay, all right. Yeah, index. Yeah, all right. Looks like, yeah, I'm wondering at one moment, we didn't pick up on this, but I think what I did is I set up index a year for some reason. Let's see if this is actually the case, right? Let's do head again. Yeah. Yeah, years used as index. Of course, that doesn't mean it doesn't have to be unique, but this is actually easier to sort and group things. So yeah, you have to be careful here if you're saving something. You don't want now. You want to save this index actually, right? So okay, so yeah, so this shows how we can extract create a new column for each document. We can create the most important words for that particular document, which signify sort of its meaning, right? So. All right, so what else do we want to do after this? Let's take a look. Columns, right. So the thing is now how to save this. We created this extra data. How do we want to save it? Well, the problem is now Parquet is not going to work anymore. So I think the best method is pickle. Pickle is like pickling your data. It's a Python, official Python provided by Python. And basically you can save pretty much any data format using pickle, right? And of course, if you want, you can also supply a zip, so it will also zip at the same time. So quite efficient way of saving your data, and it should work. The format, I don't think it should work across all versions of Python 3, probably even Python 2. So it should be still backwards compatible, right? So this is, I don't know if any other language support this out of the box, but I'm sure there's converters. That's a downside, of course. If you need to give it somebody who is not using Python, they might not be able to open it directly. They might need to have some sort of conversion. I have not explored, I don't know if anybody knows this pickle open in other languages. Anyone tried? No? Okay, so that's the downside to this. But okay, so now we have our top 10 words, right? Let's do top 5 words as well. We had top 10. Oh yeah, so this is a, yeah. So next example shows how to, yeah, using not lambda, you see, there's no lambda. Yeah, no, all right, so, all right. Okay, so top 10, now the only problem is that now all the, yeah, now I have to change to all, I'll have to change all the names, top 10 words, no. All right, let's save it. Okay. Yeah, so quick save, 1 minute, 1 second, on about 3 megabytes in size. And we have all those extra things. So again, memory usage, we're getting lots of, no, our date frame is growing up about 10 megabytes roughly, but still small enough. Now we move on to our last major embedding method, which is word2vec. This is about 10 years old, developed by Google, and still actually quite relevant. Of course, 10 years is seems like ancient in terms of machine learning in general, but it still works. Actually, still used underneath. Actually, right? It does use a neural network, but the good advantage over some of the newer methods is that it's quite fast. You can run it. You can train a large corpus on a regular, don't need a fancy GPU, don't need a fancy cluster of GPUs. You can run it on your own computer. So it basically will assign a vector representation, just like we did before, to each word, right? So here's a paper. You can read this. Actually, not very long paper if you're interested in this topic. And how do we do it? So how do we create this, right? So again, we can use GenSim. This time, convert. We're going to need the words to list, right? And we will need to, right? So those are our words, right, for sentences. Excuse me. It was okay. No, it was It was a list already, but now it's a list of lists. That's so. This column, right, contains lists of words, right? But now I want to just get to regular outside the data frame, just as outside just regular Python data structure as a list. So this toList method will return a list of the values, right, for each cell. So right now I have a two-dimensional, well, you could say two-dimensional list, right? Okay, why do I want this? Because that's what GenSim wants, right? That's it wants. It could be, again, sometimes you would gain efficiency because the way data frame is much more efficient than the list, right? Again, lists are not very efficient structures. They are very general structures in Python. They sort of like, put anything in it. So one of the downsides of lists is that you can put different data types. You can put, say, number 5, Valdis, and then a true in the same list, and that makes it for being inefficient. It's very convenient, but not very inefficient. It's not inefficient for processing large data. But for our purposes, it's completely fine. And so we have this list of sentences. Or in this case, list of documents. Let's call them list of documents, not sentence, because there's multiple sentences inside. Alice, right? And now, two of them. So how many sentences I have, right? So now I can feed them. I can feed them to this word-to-vec model. And basically, again, when you're creating this model, pay attention. Again, it's a very similar approach how we use scikit-learn. We have this word-to-vec class, and we're going to create an instance of it. So we're going to pass our sentences. And again, this might be interesting. Maybe you could somehow give it something else instead of list of lists. Maybe you can give it series. That would be more efficient. NumPy series, right? I mean, the pandas series, right? So series is actually going to be more efficient. Yeah. I mean, again, not here. It's not a big issue. But if you have millions of rows or millions of documents, it'll make a speed difference. So now, notice here again. It has a lot of options, a lot of parameters. So, for example, here you can specify vector size is 100, right? So you'll get each document will get a vector. Now, alpha window. What's window here? It means sliding window. When you go into a document, how much context should be considered, basically. Another min count. What does that mean? That means how many times a word has to appear actually to be considered all in a document, in all documents completely. If it's something very seldom used, right, it's not going to appear at all. A maximum vocabulary size, you can limit the vocabulary size. Sample, seed again, you can make it random seed, of course. Workers, this is for training. How many, if you have multi-processor support, it should work. Like you have a 1632 core CPU, right? You can supply more workers here. And what else is there interesting? Alpha, you have to read through all of them. Epochs, how much training to do? 5. If you read the original paper of Word2Vec, I think they found that doing too much training might be hurtful, actually. Right, up to 20 or 40 epochs is fine. 5 is probably the minimum to actually get anything useful. Right, so also I think probably has a vocabulary, has some other things you could do. Does it have stop words? No. Some other things too. Right, so let's take a look what we have. Yeah, so we're going to train it. It won't be too fast. It was very quick here. Right, so now of course the famous example is, which Google used in their paper, is king. So we can compare what's similar to king. And will it get anything? Well, original paper got queen. Here we have highway. Stanford, Oxford, High, Pulse. Original paper got the queen because you had a large corpus. We have a very small corpus. These are terms it considers to be similar. Now, how about queen? Right? Right. So, what does this mean actually? Right? So, in terms of Word2Vec, this means that queen, these words appear in a similar context as queen in here, right? So here we're not getting actually very good results because this is very quick training. If you have a larger corpus and you do more epochs, like we could try, see if maybe do like 20. Let me do that. Let's do that one more time. Epochs. See if this is, yeah, let's do 10. Again, but that's not going to make a significant difference because our corpus is very small. So now training is going to take a little bit longer. Again, you can see this is extremely fast, right? And now it should be different results. But yeah, Highway, Johnson, Pauls, queen. We got a queen. We got queen. Right. So we did get queen. Right. Prince as well. Right. So it's starting to work. Right. So again, so right now what we're doing is we're not working on document level. We're working on the word level. So using this model, we can compare different words because each word gets 100 long vector, which we can do. For example, like I said, this is using something called cosine similarity. We can compare them and see which one is more closer to other. So this is really fun to use, actually. Again, and sometimes that's all you really need, actually, for comparing some things, right? And it got some, before the transformers models, this actually did some significant, made some significant progress in NLP, actually. And it's still useful because, again, sometimes you need this vector. Again, the way it works is here, right? It uses window, right? What words are trying to predict what word should go inside, basically, in the context of the sliding window, basically. What else? Yeah, you can specify again the vocabulary size, how many. But here, we have only 18,000 unique words, so it's not a big issue. So sometimes you have too many words, then then it might be too much. You want to limit. Okay, now let's see. How about queen? Pulse, but queen is still okay. He got prince, but didn't get king. So it's not. Yeah. So another thing is it's not a. How should I say? Similar? No. What's the word? The relationship is not symmetrical. Yeah, the relationship is not symmetrical. So queen only got prince, right? And also king does get queen. So one thing is, again, we talked about this, I think, previously. One theory why in this particular corpus that this is the case. What is this theory? I think there are many mentions of king and queen not as a person, but as some sort of part of I don't know, building or some sort of like some other entity, basically. That's what's happening. I think there's a king something, queen something, right? So that's what's going on here. So there's different contexts than as you talk. I don't think these trials talked about king and queen as not too often. Right, so that's why this classical example, well, it works. It actually appears, right? Butler, right? So this is, again, that's what Word2Vec is trying to say. So it's saying not they are related, that they are used in the same context, basically. Now, tobacco, right? So this might be more interesting. Yeah, cake, loaf, pipe, butter, cheese, counter, ribbon, bacon, basket, right? So probably, again, somebody was stealing cake or pipe, butter, right, cheese. They were used in similar contexts. Again, we only have 1,600 documents, not enough to build a huge, very accurate model, but it is providing this context. Again, it's up to you, since you are humanities students, to provide this context and do some more analysis. This can only provide you some initial guidance, not the full blown, you can't say, okay, this is exactly, exact information. Another thing is, if we do this, let me see, if I train it again, well, no, it's always going to do the same because vector stays the same. But if I train this again, it's not deterministic completely, the building of this neural network, right? Even if I do this again with only 10 epochs, the weights will change slightly, right? So, okay, so beer. Let's do some beer. Yeah. Pint, drunk, gin, rum, ale, it works pretty well. Water, half pint pot. I'm surprised how well it works actually on this since we don't have such a big corpus. My theory is maybe that some of these longer ones provide enough context, because I don't know if you can get enough from these short documents, but the longer ones provided enough context there was some actual sentences, right? Because at 1720 we looked at, it was kind of very, very brief. Maybe by 19th century, they got more elaborate in their descriptions. So again, it's what you feed in. So if you want to do this yourself, what do you need to do? It's really simple, right? So basically, you need a list of lists or maybe a series, right? And then you can play around with it. So let's go back to this. If you want to play around with this, so you need GenSim, and you need a list of lists, again, or maybe series. Let's see if you can get it to train it on convert to series. Or maybe let's finish this notebook and then we see if we can do some extra work. We have like 15 minutes left before lunch. So we saved it. Yeah, word to vec. All right, list of lists. We don't want to do this. Until here. So word2vec, it takes you can take I think it takes a corpus file itself. So you can so not sentence, you just give it a corpus file. But then you have to read up the documentation, what the corpus file should be, some format. Again, if anybody else has done work on this, you have to look it up actually. You can maybe skip some of this part. So workers min alpha, right? It might make sense to maybe play around with this. Again, it's the advantages with this model is that you can play around, actually get the results quite quickly. Again, if you work with some more complex models, like I said, training some larger neural network for LLM needs, even BERT, it takes a while, and then you don't get this feedback. So maybe you spent a weekend training something, and it's basically garbage, right? That's a big problem with these large models, actually. So next thing is what we can do is, right, so we go to beer, okay. I want to show you what's underneath. I mentioned this is basically a 100 number vector. And again, what do these numbers mean? The bad news is these numbers don't have any meaning. They don't represent a single word. It's just a way word vector. It says, okay, you want 100 weights on it. When building this neural network, it generates 100 weights. You could make it 50, you could make it 200. The original paper says 100. It seemed like the reasonable compromise. You could probably do it even only 1 or 2, but it would be too little information. 50 could be done, be 200. It's not going to affect too much, right? 100 was just a reasonable compromise. And I've seen up to 300. Again, it's not going to affect too much speed again, but each individual number by itself does not have any significant, doesn't have a meaning to some specific word, right? So, because again, if you have a document with only 44 unique words, you got out a vector with 100, right? So it seems, how could that be? But if you build a neural network, of course, you have the middle layers and you have 100 output layers. So the output is 100, so you get 100. right? How high you want to jump, you get that's how high you jump, basically. Now, dimensions of our sentences, right? Yeah, minimum sentence 5, 1100. So word to vec is good, which we can compare different words. But there's another extension of word to vec, which is called doc to vec, right? Document to vector, right? So instead of assigning a vector to each word, we're going to assign a vector to each document. Now let's see how that works, right? So so we have a row of 1600 documents, and for each one of them we would like to assign this numerical vector. Okay, so we already have our sentences, right? So it's going to be exactly similar. We have our sentences, right? This is one way of doing it. I wonder why did I do this like this way? It will be kind of slow, but because I'll add TQDM. Yeah, this is going to be kind of slower one. I don't know why I didn't do. I don't know if it's possible to do it. Yeah, and import from T. Yeah, thank you, AI. Thank you, Copilot. On how slow it's going to be. No, not that slow. Yeah, so that's not going to be that slow. So why was I worried? I don't know. Let's take a look. Yeah, it is very quick, actually. Like 400,000 iterations seconds, so like less than seconds. So that's not the end of the world. So we have tagged documents. Again, to create this doc to vec is a little bit more complex. So we create these tagged documents. In fact, basically, each tag document object has the words inside, basically, right? So basically added the tag property, right? So now we can train it. So we create a doc to vec. Instead of 100, I'll use default. I think is 100 still. Yeah, 100. So instead of default vector size of 100, we'll use 50. Thank you, Copilot. And instead of min default epochs of 5, we'll use 40. And instead of default min count of 5, we will use 2. So this means, well, in this case, since these are actually documents, all should be different. I wonder if the min count is actually, what does it refer to? Min count. Let's take a look. Well, there's more arguments you have to read about this. Of course, you could look it up in the min count. Okay, all right. Yeah, so we want at least words to appear at least twice, right? So we assume that the word appears only once, does not have any relevance to anything else, obviously, right? So because it won't affect the comparison. So again, to show you some ways so you can adjust this model. And now the training. This should be a while. No, this not yet. This is just an instance. This is just an instance, right? Again, we have created an instance of the model, but we have not trained it yet, right? So very quick, right? Now build vocabulary. And that's the thing is we have to first, I think we have to first get the vocabulary, right? Yes. We get the vocabulary. That's also still quick. That's not training yet, right? We can see so it now provides basically king, queen, beer, tobacco. We know which one is which, basically. Now, and again, we can see, we can go backwards. 293 indeed is a king, right? Because again, we need a way of going back and forth quickly. Okay, now finally, okay, we still have some other ones. Yeah, say prisoner do me. Okay, now double check how many documents, how many epochs, 40, right? Now, so now finally it's going to take 10 seconds, at least took a while ago. So 40 epochs, right? Again, pretty quick, it should be pretty quick. So we provide our tagged sentences. total examples, right? On the corpus count, and also how many epochs. Of course, this could be just a number, or we could skip this part here. Train, epochs. No, you do need to provide at least the number here. Now, let's train it. And it should be pretty quick. 10 seconds. Well, my computer is slower, maybe. Now I was looking at better computer, maybe. Maybe the 40 epochs was too ambitious. Maybe I did 5 before, so now 5 times 8. No, yeah, so 30 seconds. I don't know how about you. How slow is it? How fast is it for you? How fast? 8 seconds. Very good. 12. 3 seconds. That's Mac, right? Yes. That's M2 or M3 or M1? M2. Very good. Very good. Awesome. Right. So now we have our model, and now of course this means that each entry of our 1600 documents, we each gets a vector. And again, that means of course we have very different ways of comparing these documents, right? For now we can use cosine similarity, but we can use some other ones, right? So none of these values mean by themselves mean anything specific, but again we have 1630, and our shapes, of course, it makes sense. So now I would like to, before we leave, so I'll assign this vector to this data frame because I want to use it later on. So let's do that. Index. Yeah. I'm going to reset the index. Yeah, for some reason I was using the year, but I can reset it. This recipe will reset the index, meaning you have a year column, it will move back to the regular column and just have a regular index, numeric index. And right, year is now a column, now it's numeric number. And now assign index. Right, we're going to use a mapping method. Now the question is, could we do anything else quicker? Because there might be a quicker way of doing this. I'm thinking, can you do it directly? Since this is a nump, so let's double check if this is actually possible to do it. This might not be the fastest because this one here, right? Let's take a look. What is it? Type, right? Let's check. Let's check the type of DV2 model DV. Yeah, thank you, AI Copilot. Print. Come on. Yeah. That's keyed vectors, but I want the first one. Now type of first entry element. Okay. NumPy then the array. I think we could do it directly. I think we should be able to do it, right? Now, right, because it's just then the array and shape. And now let's do shape. Shape of first element. 50, yeah, it's a single dimension, right? So for some reason, I'm here. We got a couple minutes before we go to lunch. This is going to be slower mapping, right? So what I'm doing is one by one. Basically, it's faster than a regular for loop, but still, it is basically a for loop here, right? So how quickly it was? It was quick. It was still quick, right? But I don't know why did I do it this way, and why couldn't I try to do it immediately? Let's see if this works. Well, this works for sure, right? And I can. Now I need, of course, scrolling. Where's my scrolling? Why is it not? What happened to my scroll? Oh, maybe here. All right. Wait. Doc to vec. Oh, there we go. This one? Yeah. Yeah, so I have my vector. I have my vector of 50 right here, right? Yeah. Now, maybe I'll do CAD. So it's pretty quick actually, but I think there should be a quicker way of doing it. I think we could skip a map and just assign the whole list, whole dv2. I think the issue directly, since it is not a list. Sorry, Copilot, that's a mistake. It's a, so it didn't pick up on, it's a NumPy array. Let's try this. But only question now, this is, I think the reason I think question is actually going to be a copy, right? Or is it going to be assignment? If you pass array, is it going to be full copy or is it just going to be an alias, right? Let's take a look if this works. This should be much quicker. Yeah, it's instant, right? So it should still be present, right? It should still work, right? Yeah, it's, well, we have a, only thing is the same, exactly the same? Yeah. Okay. Now, right, we can do the last 3 columns, right? Yeah. On numerical indexing, right? We can do things like this. Right, this is what we could do. Yeah, so this recipe is you want to make copy of data, right? Head copy, right? This is just recipe. This actually copies the data, because one thing you have to be careful when working with NumPy and pandas is whether this is actually a copy of data or whether this is an alias actually in memory somewhere else. Okay, but let's save this because I think it's a good time to finish this. Let's.
I don't think it worked, at least it didn't on my computer, because it assigned the dot to vec.
So maybe just copy. Can we do copy?
It still doesn't work.
No?
Well, try it, maybe it works.
Let's try this now. Nope, attribute error. Okay. Keyed vectors. Okay, so this we need to get it out. So why did it's, let's see where there's a mistake. So this, it's, this, because I know the problem is. The problem, this is fine. This is good. But the problem is this part here. These are not keyed vectors. It's not something pandas understands, right? So the keyed vectors need to be converted to something that pandas could understand, right? That's why I use the mapping approach. So there was, it's always, they're saying Chesterton's fence, right? I don't know if you heard of this. Chesterton was the writer, right? Father Brown series in 20th century. But he said, if you see a fence on a road, before you tear it down, you should make sure you know why the fence is there, right? So often you'll see some silly code. Maybe even yourself, you wrote some silly code, and you'll think, why did they do this? But there is a reason usually for that, right? And then you understand this reason. Maybe the reason was not correct anymore. Maybe the justification changed. Only then, when you understand why it was there, you can go and change it and take down the fence. So, with that said, I think you could basically, so this means we will have to convert this to first to NumPy, another NumPy array, basically. That's what we have to do. So, no, it's not, so that's why I lied. You see, I lied to the Copilot, right? So, yes, 1 more minute, we'll finish. All right, so yeah, so this was not, so this, I'll leave this as to do. See if we can convert, bless you. Yeah. No, so I'll do this again. Yeah, we'll redo it, and then we'll save the pickles, and we can go to lunch. I'll redo it. Again, this is very fast. Yeah. Let's double check. Yeah, it's there. Yeah, this is just a double checks. Yeah. And now let's save it. And then we can continue working on this. Yeah. Bless you. Again. Right. Okay, so let's go for lunch. I'll save this notebook. Again, all the change we did today will be reflected in the GitHub repository.